Good morning, Professor Lohman. This is tests 11 through 12, problem 14, part A. So let's start this off. Okay, so liquefied natural gas, LNG, in a vertical storage tank has a density of 455 kilograms per meter cubed. The depth of the LNG in the tank is 2 meters, and the absolute pressure in the air inside the tank above the upper surface of the LNG is 1.22 times 10 to the fifth. What is the absolute pressure at the bottom of the tank? Okay, so first of all, we're just going to start off by writing some, at the top of the page, we're going to write some useful, we know that atmospheric temperature is 1.001 times 10 to the fifth, and we know that the density of water is 10 times 10 to the third, and we're going to be using those later in the problem, so I thought that would be nice to just write them out at the top so we can have them there. Okay, so we're looking for what is the absolute pressure at the bottom of the tank. So we're going to have to add the absolute pressure of air above the tank plus the pressure of the LNG. So to do that, we're going to, we have our equation, rho, or the pressure plus rho GH. So we're going to use that, and we have the pressure is, the absolute pressure of air inside the tank is 1.22 times 10 to the fifth. Plus the density is 455, 9.8, 2 meters above. 2 meters above, so I'll put that in my calculator. Okay, I got 1.3 times 10 to the fifth. As you can see, that's the right answer. Okay, we'll go to part B. Okay, you fill a vertical glass tube with depth of 15 centimeters with fresh water. You then pour on top of the water an additional 15 centimeters of gasoline. The density is 7.4 times 10 to the second, which does not mix with water. The upper surface of the gasoline is exposed to air. Find the gauge pressure at the interface between the gasoline and water. Okay, so to find the gauge pressure, you know it's going to be the atmospheric pressure minus the pressure in the tank. We're going to get the difference from the atmospheric temperature to the pressure in the tank. So we're looking at the pressure, find the gauge pressure difference between the gasoline and water. Okay. So interface between the gasoline and water. Okay, so we need the we need to get the pressure of the gasoline and the pressure, right, part B here, pressure of the gasoline and the pressure of the atmosphere above the gasoline. Okay, so we know that as we saw, we wrote above here that the atmospheric pressure is 1.01 times 10 to the fifth. We'll use that. We'll do pressure plus rho GH So we'll have 1.01 times 10 to the fifth. And since it's the gauge pressure, it's going to be 1.01 times 10 to the fifth. It's going to subtract plus rho GH. For all intents and purposes, we'll do this first. Rho GH is going to be the density of gasoline is 7.4 times 10 to the second, 9.8. It says 15 centimeters. So we're going to use 0.15. Okay, I'll put it into my calculator, see what we get. Okay, so we get 108.7.8, which is just rounds to 1090 1.087.8, which rounds to 1090. Have that in pascals. Also, just in the previous question, it was in pascals as well. Pressure. Okay, so we got the answer right there. It's the same answer. And we don't need this parentheses. Okay, so find the gauge pressure at the bottom of the tube this time. So for finding it at the bottom of the tube, we'll for part C, we'll write C right here. We'll have to use the pressure of the water as well. Now we know that the pressure of the air, since it's the gauge pressure, we only need the difference in the pressure at the pressure of the oil and the water. So we'll just do 7.4 times 10 to the second times 10 times 0.15 plus the temperature, the density of water is 1 times 10 to the third. It said 9.8 instead of 10. 9.8 times 0.15 as well. Okay, now we'll plug this into the calculator and see what we get for C. Got 255. 7.8. And the answer is, we might have a different like rounding error or something, but that's essentially the same answer. Okay, we'll go to part D. Okay, in the open tube manometer, the absolute pressure in the container of the gas on the left is 2.01 times 10 to the fifth. Its atmospheric pressure is 1 times 10 to the fifth, and the liquid in the manometer is mercury is density 1.36 times 10 to the fourth. What will be the difference in the height, left and right column? So we're going to use the same. We're going to use Bernoulli's equation to find this. We know the pressure is 2.10 times 10 to the fifth plus rho GH, which is 0.36 times 10 to the fourth times 9.8 times H1 equals 1.01 times 10 to the fifth, the atmospheric pressure of air, atmosphere, and plus 1.36 times 10 to the fourth, 9.8 H2. Okay, there we go. Now we're gonna simplify this equation. We're gonna do 2.10 minus 1.01 times 10 to the fifth equals 1.36 times 10 to the fourth times 9.8 H2 minus H1. So we simplified it. As you can see, if we divide what's on the right side of the equation, the 1.36 times 9.8, we will get the difference of the pressures divide the difference in the pressures by the right side of the equation. We'll get the difference in the height. Okay, so H2 minus H1 equals 0.10 times 10 to the fifth minus 1.01 10 to the fifth over 0.36 10 to the fourth 9.8. Okay, I'll plug this into my calculator, see what we get. We get 0.817 meters, and it's in millimeters, so we convert that, it would just be 8.18 millimeters. Okay, so we go to part E. And the manometer, the tube shown in the figure, the oil in the right hand arm is olive oil of density 916 kilograms per meter squared. The top of the tube oil is 25 centimeters above the bottom of the tube. What is the height of the water above the bottom of the tube? Okay, here, let me grab a new page. And we'll start from here. Okay, so part E. Okay. Um, so we know that they're each going to have an atmospheric pressure of 1.01 times 10 to the fifth. On each side, we're going to have an equation for the pressure, atmospheric pressure from the water and from the oil. So we can set those equal to each other, and we'll find that the atmospheric temperature just cancels, so we'll ignore those. We'll do the pressure of the water, we'll do rho GH. The density of water is 1 times 10 to the third times 9.8. H water is what we're looking for, equals to the density of the oil, which is 916 times 9.8, and has a height of 0.25 meters. Now we can we'll divide the left side of the equation by the right side to find the H of the water, the height of the water. So let me just do that in my calculator right now. 916 times 9.81 times 0.25. Then we do divide it by 1 times 10 to the third times 9.8. Okay. We get H water equal to 0.229 meters. They have it in centimeters, so we know that just put 2 decimal places back, it would be 22.9 centimeters. That's the right answer. Okay. So we have part F and part G. Okay, it says, what is the gauge pressure 15 centimeters beneath the surface of the water? Okay, so the gauge pressure is, like we said before, the difference between the atmospheric pressure and the pressure of the tube. So we can just ignore atmospheric pressure because it's going to cancel out. So we'll just get the pressure. We'll just get the pressure of the water 15 centimeters below. So it'll be 1 times 10 to the third times 9.8 times 0.15 meters. Plug that into the calculator. 10 to the third times 9.8 times 0.15. Got 1470 pascals. That is the answer. Okay, so at what depth below the surface of the oil is the gauge pressure the same as in part F? Okay. Okay, so we're going to set the gauge pressure equal to the same pressure we got above 1470 pascals. And we're going to see what depth below the oil. So, we know that the atmospheric pressure should cancel out again. So we'll ignore those. We'll just have rho GH for each side of the equation. And we'll have a density of oil. We'll start with what we had before. We have 1470 pascals. That's from the water. We're gonna find the height. That's the pressure. We're gonna find the 1470. We're gonna have it equal to the density of oil times the gravitational constant. 1/6 is the density of oil, times 9.8 times the height of oil. So we're going to solve for the height of oil. And we will get we'll get 0.16 3, and that's meters. So we know it's 0.16, and it's asking for centimeters. So we'll just move it 2 places over. 16.3 is the answer. That's what we get. So that has been test 11 through 12, problem 14. Thank you, Professor Lohman. This is our work. Yeah, this is all the work that we just did. Just in case you had problems looking at it. And thank you for listening. Have a nice day.